And you're live.
Okay. So if you haven't figured it out yet, I'm not Arsnake, and I'm not talking about polar bears. So that's a fill in here kind of the last minute, and dug up this talk about cryptography for penetration testers, which I think should be a pretty interesting topic that doesn't get too much attention, but it's a very good technique for attacking web applications that often gets overlooked. The idea behind the title is there's a class that's taught at my alma mater called Physics for Future Presidents. And the idea behind that is that presidents need to know concepts about physics, but they don't need to know how to calculate like the acceleration of a ball dropped off a building. Well, the same sort of thing applies for cryptography. If you're a pen tester, you need to understand some really basic things about crypto and how it works and what to look for. You don't really need to understand so much about how it works and what the math is and S boxes and rounds and things like that. So the idea is you learn just enough to be able to attack applications. And that's what I'm trying to cover here. Just a quick background about me. I'm currently with Barricode. I'm running the research group over there. Previously, I've done a lot of consulting for At Stake and then Symantec through acquisition. Prior to that, a little bit of work with the NSA. So here's what we're going to cover today. And the talk was originally 75 minutes. As I mentioned, I dug it up from an old presentation. I'm going to try and fit 75 minutes worth of content into 45 minutes and replaced a lot of words with pictures, so hopefully that'll help. We're going to go over a quick overview of what the sort of problem is that we're trying to address here. Do some crypto background. Talk about general analysis techniques for pen testers, and then go into some actual case studies from applications that I've pen tested in the past, where some of these analysis techniques can be illustrated. And I think a lot of it makes a lot of sense once you actually start to see the real data from the real applications and how easy it was to actually attack. So overview. How much do you really need to know about crypto in order to actually detect and exploit crypto weaknesses in web applications? Well, the answer is, as I kind of alluded to before, not a whole lot. You need to know a few basic things about cryptography, but you don't really need to know any of the math or anything beyond that. So learn some basic techniques for identifying cryptographic data. So is it cryptography or is it not? Learn some black box heuristics for recognizing when a web application is doing something the wrong way or doing something in a weak fashion that we might be able to take advantage of. And then take some real-world penetration tests and apply those techniques that we're learning about in a generic sense and apply it to the real data and see how those attacks actually come to fruition. The talk is aimed at penetration testers. If you're a developer, it might be interesting for you too, but it is coming from the perspective of an offensive perspective. We're talking about how to attack these things from a black box scenario. I assume that you have an understanding of HTTP and common character encoding mechanisms that web applications tend to use, base64 being one of those. I assume that you have an understanding of cryptographic terms, but none of the math. And we're going to review about 5 or 6 slides that go over kind of that base crypto, just kind of as a refresher. And then finally, the case studies that we're going to cover, which there are 2 of, are from real-world applications, real customer applications, but the data has been sanitized and names have been changed to protect the innocent and all of that. So the crypto that matters in 6 short slides. This is what penetration testers need to know, my theory anyway. 2 types of ciphers, block ciphers and stream ciphers. One operates on blocks of data, fixed length blocks of data, usually 8 bytes or 16 bytes at a time. We call that a block. The block sizes vary depending on the algorithm. So for example, you can have the same algorithm such as AES, and you can use, it can support different block sizes. Different modes of operation, so it's kind of like, I want to use this flavor of DES. There are different modes that you can run the cipher in. It's still the same cipher, but it changes the way that the different blocks interact with one another. And we have the kind of the graphic describing that in a little bit more detail later. Stream cipher operates on plain text 1 bit at a time. the algorithm or the cipher generates a key stream, and then you take some plain text along with that key stream and combine those together, and you get ciphertext. We'll get into this a little bit more later. I've listed some example ciphers there that you've probably heard of before, just kind of showing you which category, high-level category that each one of them falls into. So block ciphers. We're going to talk about one particular mode of a block cipher, which is called the electronic codebook mode, or ECB mode. And this is a relatively weak mode, but it's the simplest mode that a block cipher can be run in. When you're using ECB mode, every block of plaintext is treated independently of all the others. So you take the plaintext block, you run it through the cipher, and out comes, you run it through the encryption algorithm, and out comes the ciphertext. And that's what we're showing there. You can see there's no relation between the blocks. It just, each block of plaintext goes straight down into to the cipher, and then out comes the ciphertext. There are some weaknesses with this approach. Structure in the plaintext is reflected in the ciphertext. So what I mean by that is a particular piece of plaintext, and I encrypt it at different locations within the larger piece of data, it's going to show up as the same ciphertext every time, and that's illustrated there. Assume that the two blue blocks are the same data going in. Well, you're going to get orange coming out the other side, regardless of what the neighboring data is. So if I change one block in the plaintext, only one block in the ciphertext changes. I don't know if you caught that, but it was the one on the very left there that actually changed. So the weakness here is, obviously the pattern recognition of one plaintext is always the same ciphertext, assuming the same key. But also ciphertext blocks can be modified without detection because every block is encrypted and decrypted independently of one another. So we'll talk about a little bit a different mode here that tries to address some of those weaknesses, and it's called cipher block chaining mode. And in this case, you can see instead of just having that straight down mechanism for each block where it just gets encrypted and out comes the ciphertext, now you've got, for every block that gets encrypted, the previous block's ciphertext is XORed with the plaintext, and it actually feeds in to the encryption for that next block. So what does it mean? It means when you change the message, it doesn't just affect one block of ciphertext, it affects all the blocks of ciphertext that are subsequent to the change. One other thing to notice here is, unlike the ECB mode, we've got our two blue blocks of plaintext. They don't encrypt to the same thing because of the fact that there are those blocks in between, and they're actually influencing how that cipher operates. So now you don't have that pattern recognition anymore. If I change the contents of one of those plaintext blocks, now look what happens to the ciphertext. It has a ripple effect. It changes the initial block that we're aligned with, and then that feeds into the next stage and changes the ciphertext there, which then feeds into the next stage. So as you can see, it's a much stronger mode because you can't just change one little thing because nothing else will decrypt to the right values anymore. And this is kind of an illustration of those different modes or simulation of those different modes. This came from Wikipedia, but it kind of shows how that pattern matching works, or that pattern recognition works for ECB, whereas the black part of the penguin always shows up as the same shade in the ECB mode. The white always shows up the same, and so on. Whereas CBC, because you have that chaining functionality, you actually get a more random distribution on the output. Okay, and finally the stream cipher. I alluded to this before, but it's the plaintext message being processed byte by byte as a stream. What you can see there is how the key scheduler works. So it takes a key, like the other encryption algorithms did. It takes an initialization vector, and it feeds those two in and generates a key stream. And that key stream is of arbitrary length. You can just keep generating key streams as much data as you need to encrypt. So then what you do is you take the key stream, you line it up with the plaintext, and then you simply XOR those two together, and out comes the ciphertext. If you want to decrypt it, you take the ciphertext, XOR it with the same key stream, and you get the plaintext back, and that's because XOR is a reversible function. So stream cipher is pretty straightforward. in terms of, it's a lot less complicated than the block cipher. There are not a lot of different modes of operation. It's a key stream, it's just XOR. And then finally, some common cryptography mistakes that people make when they're developing applications. One is using an insecure cipher mode. ECB, like we talked about, tends to be the default in a lot of implementations. You use the ECB mode, you end up with that codebook style where you have pattern recognition, you have cipher block replacement. But people tend to use this because it's the default, and they don't know enough to change. They're like, why would I change it? What's the reasoning for it? They don't have that background. That one in one of the case studies as well. With stream ciphers, the idea is you're not supposed to reuse your key stream, the same key stream, to encrypt different pieces of data. It's a bad practice, and it can lead to some attacks. Other things that you can, poor key selection. You always hear, when people are talking about cryptography, you always hear about key sizes and, oh, I need AES-256, or I need a bigger key size. But people don't talk about key selection. Well, if my key is 512 bits long, but I don't pick a random key properly. I pick something that's a little bit. It doesn't matter how long the if I didn't start with a good source of randomness, and that kind of goes into the random number generation one there. But also insufficient key length. Obviously, if you pick something that's way too short, like DES is a 56-bit key, that's brute forceable within trivial amounts of, not trivial, but very short amounts of time these days with the computing power that's available today. So obviously, you don't want to pick too short of a key size either. And then finally, the last big mistake that the developers make is thinking that they'll design their own encryption algorithm because know that, and therefore it will be more secure than using AES, which is a publicly known cipher. Everybody knows how it works. The algorithms are public. And the fallacy there is obviously that the security should not be based on secrecy. These algorithms that are out there in the public have been scrutinized for years, if not decades, by professional cryptanalysts to make sure that the algorithms themselves are not subject to attack. From time to time, yeah, people discover weaknesses to reduce the key space and whatnot, but in general, they've been subject to a lot more scrutiny than whatever algorithm Joe developer comes up with in a week at his desk. I've seen some really horrific things that people have designed and they think is very secure, and then you look at it and it's like just a substitution cipher, or it's just a fancy form of obfuscation. So the rule is just don't ever try to your own crypto. Use something that is, that's out there, that's public, that's been scrutinized, and then follow best practices in terms of implementing it. Okay, so that was the crypto primer to kind of refresh your memory on all the basic crypto stuff that you know. And honestly, that's all the crypto you need to know to do pen testing. Okay, so when you're doing a pen test of an application, a lot of times you run into what I like to say is gibberish. Just query strings that are just long strings of text, and cookies that are incomprehensible. You don't know what's in there. You can just see there's a lot of letters and numbers and symbols, and you don't really know exactly what it is. So that happens all the time. Post parameters, hidden fields all over the application as data is being passed around. So one of the things that you want to do right up front is figure out, is the application actually encryption, or is it just doing some sort of trivial encoding? 64 being hex encoding, are they doing ROT13 or something to just make it look unreadable? Because you don't want to take these cryptography techniques and try and apply them if it's not actually crypto that they're using. So the first thing you want to do is kind of figure out what it is. So you check for the common things first. You base 64 decode it. Does the gibberish turn into something that's immediately readable and you can see now your username or something that you recognize? Or does it just turn into more? One thing that's very effective is just to simply test for randomness. One characteristic of a good cryptographic algorithm is that the output should be evenly distributed. What that means is if I take a large sample size, so a large blob of data, and let's say it's just all text, which is, there's not a lot of entropy in text. It's all ASCII, it's alphanumeric. But if I run that through a good cryptographic algorithm, what I should get out, if I look at, if I count the number of, 00 bytes and 01 bytes and just across the spectrum for up to 256 or 255 rather, I should get an even distribution across that range for a sufficiently large sample. So there are tools out there. One of them is this ENT tool that will take an input in the form of a file, and it will calculate all these different statistics about it for entropy per byte, chi-square distribution, arithmetic mean, serial correlation, and all these things are kind of heuristics to determine whether or not the data that is being fed into it is actually random data, and we use that synonymously with is it crypto. So in the example there, I've got two files that I've run it on. First one is just a function in C. It's a SHA-1 algorithm, just source code, and it's a couple hundred lines of source. And the second thing that I ran it against is the PGP encrypted version of that same file, which should display those randomness characteristics that I described. So you can see in the first file with just the C file, I have very low entropy. The entropy per byte, there's 8 bits in a byte. The entropy is only 4.76 bits per byte. So that's saying that somewhere between 3 and 4 bits are constant across every character. Serial correlation coefficient is another one that's kind of interesting. It's basically saying that how correlated is each character compared to the one before it. So again, as you would expect with ASCII, there's a very close correlation because the alphanumeric characters in ASCII are kind of clumped together in the range from like 20 to 127. So anyway, you can use things like this to kind of run your data through and figure out if it's actually just random or not, and just make sure that you have a large enough sample size. So if it's a cookie, for example, you want to run like 100, 500, 1,000 different cookies through it just to make sure that you've got enough of a sample size. Then you start observing characteristics of the data. So let's assume that we passed that previous test and said that the data is actually random. So it came back with high entropy, low correlation. We think it might be crypto. So then you can start to look at basic characteristics about it, like what's the length of it? Is it an 8-byte blob, or is it a 10-byte blob? Is it a multiple of a common block size? If it's a 10-byte blob or an 11-byte blob, you can guarantee that it's not going to be the output of a block cipher using an 8-byte block because it doesn't divide evenly. Other things you can look at are, is the length the same as a known hash algorithm? So if you see 32 hex characters, that might be an MD5 hash. That might be a block of crypto, output of a block cipher. So you can't say for sure that it's MD5, but certain kind of magic lengths, like 32 hex characters, are indicative that it might be a hash. It might be a straight hash. It might be a keyed hash. You don't really know. Again, we're just trying to take some of these heuristics and gather information about what. Then you start with the tokens themselves. Can you affect, so you're trying to figure out which pieces of data within the web application itself affect that blob that you're looking at. Let's say, in this case, the token is a cookie. So I change my username. That cookie pieces time you might happen is I have to keep increasing my username a couple characters, and then, oh, look, it goes beyond that block boundary and I get another full block. For the cookie to change again, now then it jumps up by another 8 bytes. So you can use the sort of behaviors. I mean, if you see that behavior, that's very cut and dry, that if I've got to add 8, every time I add 8 characters, the token jumps by 8 characters. That's your likelihood is pretty high there that they're using a block cipher. And then finally, figuring out which parts of the input actually affect the output. So maybe not actually, but then I go and see I'm username, nothing's happening to the cookie. But if I change the password, suddenly we get that that block increase again. So we know now that the username is probably not stored in the token, and the password probably is. Then we say, well, how does changing the password actually affect the password? What happens? Does it change one block only, because that would indicate maybe an ECB mode, or one block? And then you can get in a little bit deeper, and you can start to try to narrow down cipher modes. Blocks in the same token, that's indicative of ECB, because that just doesn't happen by chance. There's a number of sort of these heuristic techniques that you can do across a lot of data, and just look for blocks to be repeated or blocks to show up in the same position or different positions across different tokens that can give you some insight into the cipher mode. I'm going to skip through this because I want to get to the case studies. So our first thing, we're going to talk about a block cipher that we attacked. This was a while ago, and I can't remember exactly what the context was, but I think it was like something to do with an ISP, and it was a web portal, and the subscribers could manage their accounts and do various things on it that were accounts. And the important part is that this application track user identity. So this is what it looked like when you fetched a page. This was like a My Account page, so something that you would obviously have to be logged into the retrieve. And what it's depending on there is this cookie that's being passed in every request called, in this case, it's called the EE cookie, but it contains a bunch of base64 encoded junk in it, and that was what it used to determine who you were. And it passed that over with every request. So essentially, instead of using sessions, like most applications would under normal circumstances, they were passing over encrypted form of the actual credential itself. So every time you issue a request, you click on My Account, you click on some other pages, it would issue you a new one of these cookies, which would then, of course, your browser would then issue back on the subserver. So as you're browsing through the application, you can capture a bunch of these different cookies because the server was sending you a new one every time you did something. So capturing relevant was not difficult in this case. If you're just passing proxy and then just grepping out all the cookie values. So you base64 decode them. I mentioned before that was easily base64. So you base64 decode them and you get that. Well, then we ask some of these questions, like what is the length? Is the length a multiple of what I was getting to? So we divide it by, so each one of these is an 8 block. By coincidence, if you were in one of the more secure cipher modes, like there's close to zero chance that would just happen. But what's happening here is that they've got, this is ECB, they've got the same, that block is consisting of the same plain text data in both cases, and it's just coming out the other end, and the ciphertext is the same. Same thing is happening at the bottom there in blue, and it's happening in the same sort of positions, which we don't really know what that means yet. We just know that we see repetition. So then we kind of want to figure out what's actually going on here. What is in this thing that we're looking at? And we see that in looking at all these cookies that the application is issuing us throughout the length of our login session, the only blocks that really change are the last two. Every time it issues me a new one, most of the tokens are the same. It just changes the last bits of it. So there's a possibility that there's some sort of timeout mechanism there that's an encrypted timestamp so that it won't accept that cookie after it's been stale for like 10 or 15 minutes. That's a guess. I actually have no idea what it's for. But then we get to the point where we try to apply the technique of figuring out how we can affect the token. So we start changing things in our profile. Is my phone number represented there? Is it my address? No. My username. You start changing your username, and the size of the token starts changing. So now you know that the username is probably actually stored in there because you can directly affect it based on the length. So we register a new account in the application with a really long username, 32 bytes, which is the maximum length that it would let you select for a username. And now I've got this EE cookie back that's 11 blocks long instead of the 7 block we were looking at before. So clearly I have a direct influence on the length of that cookie, which is what I just said. The token is longer, meaning the username is probably stored in the cookie. And then what's more interesting there is that we see this, again, we see this repetition that I mentioned before. You see the repetition of the ciphertext mirroring that repeated input, the 32C characters. So what you're looking at there is probably, I'm getting ahead of myself. So what we're doing now is we're going to take, we're going to do this again. We're going to do it with a 16-byte, 16C username instead of a 32 one, and we're going to compare that. And again, we're just looking for patterns. So that's what happens when I register those two different usernames. And again, you can see that repeated block. So the theory there is that the block that's highlighted must be the encrypted form of 8 Cs, because we see it appearing in both of these different, both of these cookies. Well, the question you ask then is, why don't I see 2 of those blocks for the top one? Because it is, it's a 16-byte username. They're 8-byte blocks. I should see 2 of those. Similarly, for the one that has 32 Cs, I should see 4 of those. So you think about that for a little bit, and what you eventually realize is that there's some padding. Maybe the username doesn't start on a block boundary. It starts somewhere in the middle of a block. So you don't have 4 exact blocks of all Cs. You have one that has some Cs at the end of it, and then you have one that has some Cs at the beginning of it. So we have to figure out what the padding is and actually where the username is stored in the cookie. What's the byte offset in order to start attacking it? So we want to figure out where that is. So you start creating some more user accounts, and you can just create, you can be a little bit clever about what usernames you select in order to figure out where those offsets are. So in gray, above each one of these blocks, I list the username that we chose, and on the bottom is the token that we got back. So you can see that when I start with 5 Cs versus when I start with 6 Cs, I have a different beginning block. And when I have all Cs, I still have that, the same as when I had 6. That's a little obtuse to understand just looking at it, but when you actually spread it out and kind of theorize where the username starts, I think it makes a little bit more sense. So the layout would have to be structured in this way for us to see that block in red be the same for our all C username and our username that starts with 6 Cs. The one in the middle is different is because it's got that D in it, so that changes the ciphertext. So now we know that we're using a block cipher. They're probably using ECB. The username is reflected in the token, and we know exactly where in the token that username lives in encrypted form. It's 2 characters of something followed by the username, followed by some other stuff that we have no idea what it is. But we know where the username is, and that's the important part. Okay, so now you want to become another user. So this is where now that you've done this sort of observation, this is where the attack gets formulated. So in this particular pen test, we knew via a different vulnerability that there was a user in the app called site admin. We got a list of all the different users, and this one sounded interesting. It doesn't matter if you knew this or not. Just demonstrating that you could impersonate another user is good enough. But in this one, we knew of another good account that would probably be interesting. So we knew there was one called site admin. So in order to impersonate that user, we need to have a cookie, an encrypted cookie that corresponds to that user. And that cookie would take the format that's shown here. It's 2 characters of we don't know what, followed by site admin, followed by more of stuff that we don't know. All we care about is replacing the username. So we register more user accounts. It's nice that it lets you set up as many accounts as you want. So you register one account that just starts with site add so that you can get that first block. And then you register another account that has the MIN part of site admin at the right location in the username. So just a bunch of ones for padding, and then the MIN. And now you've got some ciphertext out of that that you can use. So you take those two, you kind of put the pieces together, and you create a new cookie using those two pieces of data. And now suddenly you can provide this to the application. It's just going to go through and decrypt it. It's going to decrypt properly. The correct characters are going to be in the right place. It's going to parse the username as site admin, and it's going to allow you access to that application as if you were that user. So a pretty standard impersonation attack. So the recap from this is that you notice that we were able to subvert the entire authentication mechanism of this application without knowing anything about the crypto that they actually use. I still don't know to this day what algorithm it was. I have no idea what the key was. I have no idea what the key size was. I didn't have to brute force anything. We just looked at patterns, and we looked for some weaknesses in the way that they had implemented and then took advantage of those. I mean, the root cause of the vulnerability is that they used ECB mode as opposed to CBC. If they had been using CBC, we wouldn't be having this conversation. So it's not like it's a complicated root cause. There was no verification mechanism, so there was no sort of like integrity check at the end of the cookie, so that if I change part of it, that the integrity check doesn't match. If they had had an integrity check mechanism, that would have stopped the attack as well. Poor design was an issue because, like I mentioned at the beginning, they should be using sessions for maintaining authentication state. You should authenticate with your user and password once, and then you get a session, and you keep passing that session back and forth, rather than passing your username in encrypted form every time. So that's kind of a poor design issue. But ultimately, ECB should not be used because it lets us do this sort of ad hoc inline substitution and like mix and match the ciphers together to come up with what we want. So that was a block cipher. Now let's look at a stream cipher. So this context was public-facing multi-tenant web application for a major financial services company. You could do a lot of stuff in here, including managing your accounts. I don't think it was a brokerage thing, but you could conduct some transactions. You could see your old statements and just information about your account. This thing was using encryption all over the place. Every parameter that was passed, every link that you clicked on had these humongous parameters in it that were all, potentially ciphertext. So they looked like what we're seeing here. So in our URLs, in our links, we saw these long things. So like statement and view statement page. I'd see these long, identifiers for statement. And there were other things, file, context. There were a bunch of different parameters that all kind of used the same, or what we assumed was the same mechanism. The URLs changed every time you logged into the application. Even if you're the same user, you log in once, you get the links were like that, and then you log in again, and the links would be totally different. So it changed per logon and across different users. So they were never the same across users. So they were doing something very aggressive with their encryption. So we picked one part of the application to take a look at, and it was the part that was dealing with viewing statements. So you could view your old bank statements or brokerage statements. And we knew what the statement numbers were because that was displayed to the user in the browser. You would say like, show me statement 704 or whatever. And then the link to that, when you clicked on the URL, was actually contained the long token there. Yeah. So we gathered a bunch of these together and took the known. So this is a known plain text, right? We know what's probably being encrypted. It's probably the statement number, and then we know what the ciphertext is because it was present in the URL that you clicked on. So we started to look for some correlations between the statement number and the ciphertext. And again, this is after the base 64 decode, which is probably obvious. This is just the hex representation of those same tokens. So we noticed that when it started with, certain characters, 704432, you saw that same structure reflected in the statement token. So that's indicated there by the colorization. And then similarly, you could look at, okay, when I have a 2 as the second to last character, a 68 shows up at a certain spot. So this is just picking up that we're seeing patterns between the plain text and the ciphertext, and it's recognizable. The same character in the plain text yields the same character in the ciphertext at that position. So all of that combined with what was on the previous slide kind of indicates to you that it's a stream cipher. Because again, you're not seeing entire blocks changing at a time. You're seeing single byte changes. What we need to do to really crack a stream cipher is to figure out what the key stream is. Remember from the original slide, we have the plain text, it gets XORed with the key stream, and you get the ciphertext. So we want to figure out what the key stream is, because that's kind of like the keys to the kingdom in this case. So you take one of those tokens, the encrypted tokens, you XOR, that's the part of the token that we think corresponds to the statement number. So we just XOR them together. And theoretically, if it's a stream cipher, what you get out of that XOR should be part of the key stream. That's a theory at this point. So then we take that same thing, we take that 10 bytes of key stream that we have, we XOR it back with a different token, just to kind of make sure that what we get out of that XOR operation matches up with the plaintext statement ID that we expect to get out of it. So just to kind of see if, okay, maybe this actually is key stream. And that checks out. When you XOR it back, you get back the number that you expect to get. So now it gets a little bit more interesting. You take that same key stream, that same 10 bytes. Now we don't have the whole key stream, we just have 10 bytes of it because that's the only part that we figured out so far. And we take that partial key stream and we XOR it with a different token. So remember I said that there's a statement token, there's a file token, and there's all sorts of different tokens that the application was using. So now we XOR it, partial key stream, with one of those tokens, and we see what comes out. And it comes out as ASCII, which again, these things don't happen by coincidence. It all comes out as alphanumeric. Okay, well that's interesting because, if you've ever watched, Wheel of Fortune, you can kind of fill in the blanks and kind of figure out what's on either side of this. And especially seeing as the link that we clicked on that corresponds to this token was the personal information link, right? So that helps too if you couldn't figure it out otherwise. So now you kind of extrapolate. So you say, okay, well I think that the plain text for this section of the token reads personal information. So I just fill that in and I XOR that with that token, and what I get out is more key stream. So because I've kind of extrapolated the plain text there, I've now got something like 10 more bytes of key stream. So now I have 20 bytes. Great. Repeating that because I've got all these different tokens to work with. They're reusing this key stream all over the place in the application. So I can just these tokens and XOR them with my known key material and just keep growing the amount I know of the key stream. So I do it with a different one called file, and I get out this string. It helps to know that we're in a section of the application clicking through it called paychecks, or called, actually it's a help section, it's called the help center, and it's the section about paychecks. So you extrapolate that. File retrieval here too, because they're passing just an encrypted file name in and pulling that off the server side, so it's actually another vulnerability. But for the purposes of this, it gets us 6 more bytes of key stream. So you just keep repeating that over again until you have not the whole key stream, because like I said before, the key stream can go on and on forever, but you get enough of the key to where you can decrypt anything in the application. In this case, it was about 200 bytes of key is as much as we needed. So then we want to figure out, again, now that we can do that, what's the actual attack? Well, the attack is being able to create tokens of your own. So what if I want to look at somebody else's bank statement? I want to be able to do an attack to where all I need to know is the statement number, and then I create my own fake statement token using what I know about the crypto, pass that in, and hope that the application returns back to me that person's statement. So I decrypt some of the statement tokens, and you can see I listed 5 of them there. That's actually what's inside it. Don't know what most of those numbers are, but you can see that in the third field there, delimited by the pipes, is the statement number. And the other stuff, you know, they might be user IDs, you know, no idea, but I know the part that we care about. So in theory, we should be able to take one of those and simply replace the token number, the statement number with another statement number that we know is valid, or just iterate across until we find one, and then view the contents. It didn't work. So then we looked at the token a little bit more and realized that at the end there was actually, you know, it was not numeric, it was actually 4 bytes of base 64 encoded. If you base 64 decode it, that's what you get in parentheses. So it looked like some sort of integrity check, except when we looked up kind of what sort of integrity check is there that generates 24 bits, we realized that it was just it was a CRC24 algorithm, which is not intended for, you know, it's intended to detect transmission errors, not to be an integrity check to prevent against manipulation. So there was like 10 lines of code on Google that you could find a reference implementation of CRC24. So now we can calculate that part too. So once we did that, it worked. So all you have to do is take a token that you found, decrypt it, change the statement number, calculate the CRC using reference code, encrypt it back using the key stream that you know, and then base 64 encode it to become a statement token. And then that worked because all the pieces kind of fell into place. All the things that the application was looking for matched up properly. So again, the thing to really take away from this, if nothing else, is that we're able to subvert the encryption mechanism of this application without, again, ever knowing what algorithm it was that they used, ever really knowing what key got fed into the RC4 algorithm, or it turned out to be RC4, we found out later, but all we knew was the key stream. We didn't know what the actual key was, but that's fine, and we didn't know any details of how this was implemented. We just looked at the patterns, and we looked for similarities, and you know, start changing what happens. So this was RC4. It was a unique key generated for each user session that ended up not really mattering, as you see. And the root cause, again, is the fact that they reuse the same key stream to encrypt a lot of different stuff. You're not supposed to do that. Stream Cipher, you're supposed to generate a key stream, and you're supposed to use it to encrypt one thing, and that's it. And they were reusing it all over the place. So that was the bad practice that led to this sort of attack. And then the fact what they had for an integrity check was a CRC24, which is not intended to be an integrity check. There was nothing secret about it. It was a reference algorithm, so it really didn't add any security. So that's the second case study. Happy to take questions. We have about -1 minute for questions. And I think the beer starts coming out soon, so that will probably make it even less possible. But contact information. Sorry?
Maybe not the beer, but the raffle.
Oh, the raffle. Okay. Really, some things are more important than others. So contact information, I'll be up here afterwards as well. I'll take a couple of questions if people want to ask them.
Can you apply the same techniques for like file encryption?
For file encryption, I mean, you could certainly look at encrypted files and do the same sort of heuristics and see if the same block appeared, like the ECB sort of thing. If you saw, and actually in files that actually might be pretty applicable because you might have a lot of white space. If you had eight space characters getting encrypted and you kept seeing that same block reappear over and over in the file, the encrypted file, yeah, that would tell you that they were using that mode. So yeah, absolutely. Was there one more? No? Yep.
With the first attack, the ECB, if the username you want to steal fit within a block, would you then not have been able to perform a similar attack because they take part of the...
Yeah, if it had been like a, let me think about it. Yeah, if it had been like a 5-byte or a 6-byte username where it all would have fit in that first block, then yeah, we wouldn't be able to do that because we wouldn't have been able to create an account by that name. So yeah, exactly. So in this case, we were lucky that it was 7 characters or longer. So, okay, thank you.